So, okay, it's second part of this video, and in today's session, we have to focus on what is semiconductor physics and semiconductor material. Okay, let's try to focus on that values. Okay, so let's see what we have. So in semiconductor things like so in this chapter we have to understand the energy band in silicon, intrinsic, extrinsic silicon, carrier transport in silicon, diffusion current, mobility, resistivity, generation, recombination or carrier cover. Okay. So first of all, we have to understand what is semiconductor material. Okay. So we have to explain what is semiconductor material. Actually, in general, we can classify insulator, conductor, and semiconductor depending on their conductivity levels. Okay. So first of all, the insulator, as we know that the insulator offer a high resistance that to flow the current through them. So resistance, typically insulator through which we cannot pass the current because it have a high resistivity. And in order, okay. So valence cell that is the outermost cell are referred as a valence cell, and the valence cell are tightly bound to the atom. So there is no free electrons that can move through that material. Okay. Some of the popular insulators are glass and quartz. Okay. So in the second part, the band energy structure of insulator, as we drawn below, you can see that the greater than 5 electron volt between the valence and the conduction band. For example, this one, because of the large forbidden and the band gap, there are very few electron in conduction band, so no conductivity and poor insulator is a poor in conductivity. So increasing the temperature, as we increase the temperature and the applied electric field is insufficient to transfer the electron from the valence cell to conduction band. So valence band, valence band, the valence electron and conduction band. Okay. After that, we have to know about the conductors. What is conductor through which offer the less resistance as compared to the insulator. Okay. Good conductor are the copper and the resist. After that, we have to know about what is semiconductors and metal that have the conductivity level somewhat between the conductor and insulator and resistivity level there. Okay. Two of the most common semiconductor are silicon and germanium. Okay, one of the most example are some gallium arsenide, indium phosphate. Okay, and as we look as a band structure of semiconductor, the forbidden gap is um, like, okay, so there are now free electrons that can move from the influence. The free electron can move in the influence of applied electric field and the room temperature. Okay, and this is nucleus. This is valence electron. This is nucleus, as you know. And the conduction band, the forbidden gap between these less than 1 electron volt. Okay, free electron at room temperature, valence electron here. So there's two type of semiconductor as we see. So in this discussion above, it is assumed that there are no external atom added to the parent semiconductor. Such semiconductor is referred as the intrinsic semiconductor. No external things is added to the parent semiconductor, so it is known as the intrinsic semiconductor. Certain impurities, when added to the intrinsic semiconductor material to increase their conductivity, such in semiconductor with the added impurities are known as extrinsic. So if we add any impurities to the semiconductor, then it becomes extrinsic semiconductor. Okay, intrinsic and extrinsic semiconductor as discussed below. So intrinsic semiconductor is a semiconductor with a very low level of impurities concentration. intrinsic semiconductor are a semiconductor with very low level of impurity concentration. They are essentially as pure as the available through the modern technology. The impurity level of is approx 1 part per billion. Okay. Conduction in intrinsic semiconductor is either due to the thermal excitation or due to the crystal effect. Okay. Silicon, germanium are the two most important semiconductor use, and other important include gallium arsenide and the indium anti antinomide. Okay, so what is the structure? Okay, how the structure look like? Okay, how the germanium has a 4 electron in the valence shell. So we do not need to discuss the how the crystal structure look like. So we have discussed that the types in which intrinsic semiconductor is further as a intrinsic semiconductor in which no impurity is added. So it's further classified as a diode band gap and indirect band gap. Okay, in diode band gap semiconductor, the maximum energy of the valence band occur at the same momentum with the minimum energy of conduction band. Thus, in diode band gap semiconductor, electron present in the minimum energy level of the conduction band. Okay, so in diode band gap, some energy is required to transfer from the conduction band to electron. But in this indirect band gap in which extra energy plus momentum is required to transfer this one. Okay, in intrinsic semiconductor, number of holes are equal to number of electrons. Hole and electron pair are generated by the thermal agitation and disappear due to the recombination. Okay, so formula is again electrical property. Semiconductor is a bipolar devices. What is semiconductor? So actually semiconductor is a bipolar devices that is both electrons and hole contribute to flow the electrons. Okay, it may be mentioned that that material are unipolar devices. The metal are the unipolar, that is only electron act as a current carrier, but in semiconductor both is a bipolar device in which electron and hole pair both act as a devices to contribute the flow of current. Okay, in semiconductor there are two different mechanism of the current flow: electron flow in the conduction band and holes flow in the valence band. Okay, electron flow in a conduction band and the holes flow in a valence band. Okay, when the external potential is applied, the free electrons are either contribute to this one. The first component contribute the electron hole. Okay, so the mathematical expression for the current density in this material is n mu and pu mu p. Okay, so after that, so the final intrinsic semiconductor, we have to find the current density as a mu n mu p, this one. Energy, the forbidden gap is also known as the energy band gap in semiconductor, depend on the temperature and decreases with the increase in temperature. Okay, Fermi level, the probability for what is Fermi level? The probability that an energy level, the probability that energy level in a semiconductor is occupied by electron is given by this expression. The probability that the energy level in the semiconductor is occupied by the electron, the given following expression will given this one. Fermi level actually represent that the energy state with the 50% probability of being filled of electron. If no forbidden, yeah, or energy band exists in an intrinsic semiconductor at the absolute zero temperature, the probability of finding the electron in valence shell. So we said that in valence shell and conduction. So at a zero temperature, we can see the temperature 100%. Probability of finding the electron in the conduction is 0%. So for me, the formula intensity is an absolute zero is a center forbidden gap. Okay. The Fermi dipole probability of this absolute zero is equal to this one. conduction plus valence by 2. Okay. Whereas two type of extensive semiconductor. So intensive semiconductor has a limited application and because very small amount of current is flow. So by adding a significant amount of impurities to pure semiconductor, the impurities are added to the some approx this one. Okay. As the conductivity increases, the semiconductor material property, as the example, the conductivity increases to the 100 or 1000 times. So, and after adding, they are divided into the two type of an extrinsic semiconductor. Okay, if added impurity is pentavalent, so added impurity is pentavalent, so that resulted in the entire when trivalent, then p type. Okay. Okay. Okay, these are the electrical properties after that. Or P type. Okay. Mass formula we know that. Hall effect. What is Hall effect? So we have to know what is the Hall effect. So Hall effect is a phenomenon by which the potential difference is created. The potential difference is created the opposite side of the conductor when it placed in a in a magnetic field. Okay. So what do you know? Hall effect is a phenomena in which a potential difference is created on the side of the opposite side of the conductor when it kept inside the in a magnetic field with the current flowing in the perpendicular direction. Current is flowing in the perpendicular direction. In a perpendicular direction. Okay, you can see the current is flowing in a perpendicular direction. We have to create a potential difference across the opposite direction, this one, and the current is flowing in the perpendicular direction to the. Okay, so stated difference is this one, Edwin Hall describes this one. So, so if a current is current in the positive x direction and b in the z direction, the force exerted in the current in a direction, thus the carrier accumulated on the b for the p type and the whole accumulated on the side of b. So okay, similarly inside the conductor. Uh, conductor and electron will accumulated on the outside of B. Thus, A will be more positive than B, and the magnitude of the voltage will depend on the carrier concentration. Thus, the Hall effect can be used to determine the carrier concentration, whether the semiconductor is P type or N type. The Hall effect potential is defined as the Beer D. So, BT is the magnetic field current, and R. What is the R? So, the R is coefficient. So B is the magnetic field. B is magnetic field. Okay, and R is the Hall effect coefficient, and D is the width of the semiconductor. So how we find the Hall effect coefficient? So by N and Q. Okay, when N is the electron concentration, Q is the so N is the electron concentration and Q is the electron charge. It explains concentration and it is charge. Okay. For the semiconductor, both with the both positive and negative charge, the Hall effect coefficient become a little bit different, in which the concentration minus n1 minus p of p minus by charge electron charge into the n plus p p the whole square. Okay, p is the electron mobility and holes mobility. Okay, Hall effect is used to design the instrument such that the magnetic field meter, Hall effect multimeter, and this magnetic field meter are used to measure the magnetic field. Hall effect multiplier. So it is used to design the instrument such as it On the basis of Hall effect, we have created many instruments. We can measure the electric field and the Hall effect multiplier, all these things. Hence, I and B are made proportional to the two signal. Okay, and we have to discuss the what is drift and diffusion carrier. Okay, so the current in a semiconductor, is a sum of, actually the current in a semiconductor is the sum of the drift plus diffusion, as the opposed to the conductor where the current flow only due to drift phenomena. As we discussed, drift current is what is different. So drift current is due to the proportional gradient of the semiconductor and given as this one. This is equal to, and this is the mobility P holes and the concentration of the holes, concentration of this one into, where J is the current density. Okay, you can find current density this minute, current per unit area. Okay, that's why ampere per centimeter square. The drift current due to the holes is equal to concentration, mobility, okay, mobility and uh, electron, electron, electron. We can say that it is the where we have studied recently. We have studied what is E. So actually, it is the electron charge. So okay, electron charge for the holes, and the whole diffusion current is given as diffusion current as whole diffusion current is minus q dp by dx. Dp is a diffusion current and a constant cells in concentration and a variation in the whole concentration. So increasing distance, the negative whole concentration increases. The total, the total, and the total whole current density is given as this one, and total electron current density. Okay, so till we have see the current density due to the drift and diffusion, conduction, conductivity, and all the things formula, and the and what is Hall effect formula, Hall coefficient. Okay, different drift current, formula. Okay, okay, diffusion constant and the carrier leader. Okay, total whole current is given as this one. For Fermi level, we can also say that EF is equal to EV plus KT ln V. Okay, so we have covered this chapter. So in next lecture, we have to discuss the semiconductor diode. So for now,